Thank you. So thank you for the invitation. Thank you to Sembra and to all the Brazilian friends for the opportunity to present here the underwater system at IFREMER. So my presentation will insist on the R&D and operational use of HOV, autonomous underwater vehicle, ROV, but also new hybrid systems. So I will get to talk about all these systems. So just a reminder, so IFREMER is a French integrated research institute for the exploitation of the sea. It's about 240 million euro budget. We are 1,600, and we are located in 25 places in France and abroad. We have 8 ships, with blue ship and coastal ship, and a full set of underwater systems from HOV to AUVs. So the mission of IFREMER is first research in different way, living, mineral, and energetical resources. We are working also on climate change, environmental studies, technologies, etc., etc. The second mission of IFREMER is survey and monitoring of resources and environments on the side of policy support, etc. And the third mission of IFREMER is a national mean agency for oceanography. So we offer ships and tools to the oceanographers in France within this system. So this system is also linked to valorization, innovation, and links with industrial and navy sectors. And in the field of underwater technologies, in our history, we start with the first laboratory, the laboratory of, the Archimede laboratory in the 60s, with the Navy and the French CNRS. This is our gen. And we move with Cousteau to more actual systems for deep sea intervention. We have worldwide targeted cooperations, and as today we are in Brazil, first spot on Brazil-France cooperation. So for Brazil, France is the second scientific partner after the US, and for France, Brazil is the first partner in South America for scientific cooperation. So we have a lot of strategic partnership, reciprocal and multidimensional activity, concluded in 2006 in a wide sense, military, spatial, energy, economy, education, etc., and a specific one in oceanography. So France and Brazil have signed a scientific and technical agreement in the field of marine science since a long time, with joint program links to CIRM and IFREMER. Today, we have a cruise of Brazil with our ship Atalante, with a seismic set, with Petrobras and University of Brasilia and Lisboa. So that's for the context. So now I'm moving to a presentation of the oceanographic mean agency side of IFREMER, and mainly a presentation of the underwater systems, because that's the topic of the workshop today. So it's, as I said at the beginning, for us it's an integrated view with coastal, regional and global systems for ship, but also for the tools. And it's not only ships and tools, it's also something related to the services we can produce for the scientist. It is to say data management, it is to say mapping, it is to say expertise around the data collected by the system. So it's a full integrated system from the engineering of the system, the maintenance, the management of the cycle of life of the systems, and the management of the data produced by the system. That's why we call this integrated view. It's optimized for science, service, that's our duty, but it is also optimized for socio-economic valorization with industry and also with the Navy. So I start with a quick presentation of the fleet. So we have 8 vessels, blue ship and coastal ship. So we have 4 blue ships, le Surroi, le Pourquoi Pas, which is the main one. We have a picture here of the Pourquoi Pas, and the more recent one. It's 107 meters length ship. And this ship is owned by IFREMER, it's operated by IFREMER, but it is also operated for the French Navy Hydrographic Services, SHOM. So we share the time of this ship between the Navy and the scientist. So that's the first view. Now I skip to the underwater system. So we have a full set of operational systems in the underwater fleets. I start with a HOV no-till, which is a 6,000 meters depth system developed in 1985. I will describe it in detail. We have a set of deep remote operated systems and deep tow. So here you have Victor 6000, which is a deep ROVs for 6000, but we have also a deep tow system, I will explain. We have a new set of hybrid system. We call it HROV. I will explain what it is later, and H-glider. And we have a full set of instrumentation, seismic, coring systems, etc., geotechnical tools. We have a set of autonomous underwater vehicles, which are in operation since 8 years now, for 3,000 meters depth, this one. Asterix and Idefix, and a park of gliders. We have 12 gliders in the fleet, plus some USV, mainly for research. And we are also engaged in technology in the design and the operation on underwater observatories, cable observatories, or non-cable observatories. So in detail, so I start with a presentation in terms of TRL, technology readiness level. So for the operational tools, we are at TRL 9, and we have also a set of R&D tools developed to prepare the next generation of operational tool, mock-up or demonstration vehicle. So I start with the operational one. So again, from survey to intervention, the first and the oldest one is the HOV no-till. Again, the set of ROV and cable system. So here you have Victor 6000. Here you have a penetrometer. It's a geotechnical tool. This yellow point here is a diver, just to give you an idea of the size. So this system is a 4 tons VR system, and we push a CPT sensor in the sediment to evaluate the density of the sediment. So it's geotechnic. It's an heavy system. And we have deep tow. In the autonomous world, we have 2 AUVs for 3,000 meters depth, developed in co-design with a Canadian company since 10 years, and a set of gliders, mainly American gliders, but we are also now developing French and European gliders. And in process, we are designing a new hybrid system, which is an ROV, but also an AUV, I will explain. And we are designing the system because for us, one of the key issues in the development of such system is the cost of operation. And the cost of operation depends on the ship itself. So if we can deploy these systems from smaller ship, it's better for us in terms of cost. So I will explain. So all these systems are fully operational. The rate of usage is about 100 dives a year per system, for no-till, for Victor, for the AUVs. And it is very important because we can have systems, if we have no activity, it costs a lot. So the activity and the rate of usage is important for us. This line is just an illustration of several R&D projects we manage in cooperation with several industrial partners in France. So this one is an intervention AUV. It's an AUV which can dock on a garage on the bottom. This one is a full autonomous AUV, with manipulator, I will describe. But we work also on USV, gliders, and crawlers. So these systems are not fully operational for us. They are just demonstration of concept and innovation. Our clients, the first is oceanography, because we are paid by the Ministry of Research in France to get about 900 days at sea with ship and equipment for the community, the scientific community. So the scientists claim for campaigns, and they use, if they are well evaluated, the ship and the submersible. But we work also for other science. This is an illustration of a neutrino telescope, which is moored in the Med Sea by 2,500 meters depth. So we have a cable to the shore, we have junction box, and we have line with photomultipliers in glass sphere to observe neutrinos. So it's astronomy. We do the job for them, installation and design of these systems, but they pay us to do the job because they are not from the oceanography. So it's a services for us. This is an illustration of an ancient wreck of Louis XIV king in France. So it's archaeology. We do also archaeology for archaeologists, but they have to pay for the mission because they are not concerned by oceanography. And we have a lot of cooperation with industry in the offshore, with the oil and gas, and also mineral resource industry, in the defense area and in the rescue area, as you know. So that's for the general presentation. Now the aim and the color of my presentation today, it's about CapEx, OpEx, TRL, efficiencies, disponibilities, so it's very serious. It's not very sexy, but it is very important for us. Because to pay for a new system, it's very easy to have the money from the government, but the running costs in time, it's something which is more complex to manage. So when we decide to build a new system, the first point for us is to define the rate of usage. It's stupid to invest a lot in a submersible which will never dive. So for us, an operational system must be designed taking into account the number of dives per year. But we have also to define the TRL, okay? The operational performances, the number of publications, it's an issue for us. And also, because we're at sea, quality, health and security, etc., etc. So all this stuff is important at the beginning before we decide to invest in a new technology and in a new operational system. So for each of the system I will describe now, I will get some numbers in terms of CapEx, OpEx, rate of usage, and cost ratio. It's the cost of the underwater system slash the cost of a ship to launch the system. Because if you launch a small system at 10k euros with a big ship at thousands and thousands euros, there is something strange. Because the cost at sea, it is the cost of a ship. And the good management of these two systems is very important. So I start with no-till. So no-till is fully operational since 25 years. TRL is at 9. But no-till has all the HOV dive during the day. It's very limited, the duration of dive with manned submersible. It's about 8 to 12 hours on the bottom. And we need to have a big ship with a big A-frame to do that, so a specific ship. If a ship is just engaged by the HOV, during the night, you pay the ship for nothing. So it's why, more and more, we have strategy of using HOV coupled with AUV. The AUV is preparing the map of a dive during the night, and in the morning, we select the target, and we can deploy the no-till directly on the target, not losing time in survey on the bottom. So it's a way to optimize the OpEx. As I say, we are design authority, so the cycle of life and the management of cycle of life and the management of overall must be included in the price of your full system, and we do that. So we have some vision here of a system. So the keyword is to optimize the dimensioning of a system related to the fact that you need a special ship to operate such HOV. It's not a standard ship because the airframe is 22 tons at sea. So no-till is 6,000 meters depth rated, and in 29 years we have more than 1,800 dives. This is the mean time on the bottom, around 9,000 hours spent on the bottom, and this is the mean depth. It is rated for 6,000 meters depth, but the mean depth after 30 years is 3,000 meters depth. And the time on the bottom, it's around 7 hours. This is the number of dives. This is disponibility. So on the 1,800 dives, we never cancel a dive. And we have sometimes some interruption, only 4. So disponibility is very important because of cost. Running cost of no-till, it's 5% of the CapEx. It is to say the price you will pay no-till per year. Because you have to pay people, you have to train pilots, and this is a recurrent cost. And this is the CapEx per dive in full cost ratio. Rate of usage, it is designed for 100 dives a year. Sometimes we have less, sometimes we have more, it depends. And the cost ratio is 0.5. It is to say if a ship costs, let's say, 20,000 euro, the no-till costs half. It's not the right numbers, but just to give you an idea. So some view of no-till, we dive on Titanic, we operate some strange operation on Titanic, recovering big pieces of Titanic. This is an illustration of a titanium sphere. It's quite different from the others. We have 2 dummy spheres. We can open this dummy sphere and get out all the instrumentation for overall, which is very practical. And this is a view of the internal aspect of no-till. And here you have no-till on this workshop. We have a trailer here on the Pourquoi Pas with a garage on the Pourquoi Pas, because when this system is programmed, he's going away around the world for 1 or 2 years on the ship. No-till spent 20 years in time on the deck of a ship. So it is designed also as something which is on the deck of a ship, which is rolling and moving. So this is some illustration of the couple of no-till and the AUVs, as I say, to optimize, and some view about the interest of HOV for science and the complementarity of HOV with ROV and AUVs, as discussed by the others today. Just a story about Curiosity and Man on the Moon and Man on the Bottom of the Sea. Some geologists said the cost of Curiosity is 10 times the cost of this mission with a man. Because for the same task, collecting samples, Curiosity takes 10 times than the Man on the Moon in time on the Moon. So if you have time, no problem. But at the end, to compare the efficiency of robots and man, you have to compare all the cost of development and all the data collected by the missions. The number of data collected by Curiosity is limited for concrete data, but it's high for numerical data. So it depends what you want to do. In exploration, for us, no-till is much more productive when you dive on a site you don't know than a robot, because the man is there, and the productivity of man is better than productivity of algorithms to select what you want to do when you don't know what you want to do because you are in exploration. So that's the reason why we keep no-till in activity in our fleet. So no-till is fitted with a small robot, which is named Robin, with an umbilical, 70 meters, to get inside the wreck when it is dangerous, because it's a manned submersible, so we cannot expose the divers to risk. ROVs now, so we have a deep sea ROV named Victor 6000. So we have comparisons. In 16 years, 62 missions, 500 dives, the same time on the bottom as no-till, because we can remain on the bottom day after day. The maximum duration of dives we have with no-till is 3 days. 3 days on the bottom, because you have people on the ship, and you can imagine a relay of people. You have a numbers comparable to no-tills in terms of means of immersion and time on the bottom, but the maximum time is 100 compared to 6 hours or 4 hours on the bottom with no-till. So productivity is better, and another difference is the payload. On no-till, we are limited to 100 kilogram payload for scientific experiments. On the ROV, we can have up to 600 kilograms dedicated for science, and the weight of the vehicle is 4.5 tons compared to 20 tons for no-till. So it's more compact. We have more capacity in terms of boarding different scientific equipment. It's more versatile. That's the advantage. But we have some disadvantage because the productivity on the bottom is lower, but we have more time. So we have to take the time into account in the comparison. So we can deploy no-till through Victor, through A-frame, through crane. It's more easy to deploy, but you have to manage the cable, the dead weight, the umbilical, and you need to have a DP ship if you want to operate in depth with such dog on the leash. So we have also some constraints with the dog on the leash concept. But it's more versatile, and we can easily change the components, which is less feasible on no-till. On deck of a ship, you have a PC room, and I just show this picture because around this PC room, there is the integrated data management, which is very important. At the end of the dive, the client, the scientist, can go back with a hard disk with all the data, technical data, numerical data, image, sonar image, on a hard disk, and he can replay his dive at home. So some image of deployment of Victor, an image of operation of Victor on the neutrino telescope. On Victor, we have two manipulators, a 7-function manipulator, hydraulic manipulator, very precise one, but also very expensive to do very precise science or more industrial things. So we have some view here, and again, the deployment by the A-frame or by the side. So the constraints for such ROV, deep sea ROV, we have also constraints on the ship because we need the DP, the dynamic positioning. We have less constraints on the launch and recovery system, so it's comparable at the end in terms of cost. So the TRL is at 9. The rate of usage is about 100 dive a year, but the dive can be up to 20 hours as a mean value. The cost ratio is better than with no-till, but the productivity is higher, 24 hours. To operate in 24-hour scheme, we need 8 crew. In fact, it's free each time. We have all the data services, data processing, telepresence, telescience. We can operate and follow dives from the shore using satellite communication. We have some haptic command to optimize the telemanipulation. We have some instrumental flexibility. As I say, the tool sled, it's exactly the same view as in space. You have a launcher, the ROV, and you have the satellite, the tool sled. And for science, it's better because we can prepare in advance the scientific payload. It's adapted to precise intervention and very high resolution mapping and high definition 3D mapping. We have a 3D also on Victor. Onshore, you can follow the dive if you have a link through for some telepresence activity, telepresence systems. It's good for public outreach and sharing the dive with different scientists. And we have 3D vision integrated also in the function of such system. So this is some example of very high precision mapping. So we have multi-beam. We develop special cameras to be able to have long-range optics. So these pictures has been taken with a few lights at 10 meters from the bottom. And we have this kind of application. This is the services we can get to the scientist to build 3D things. So all this mapping, optical mapping and acoustic mapping is done in real time, and we have all the software to get the informations. In the family of cable system, we have also deep tow. So I just present this one, which is an innovative one. It's a seismic source. So this is the seismic source. So it's an acoustic system. The emission is very low frequency, 300 Hertz. Each second, we emit at 300 Hertz up to 186 dB. So it's a very huge power. And the idea is to avoid to do seismic with air gun from the surface and to avoid to ensonify all the water column. We are faced to problems with the acoustics in general, with mammals, with regulation, and this project, the idea is to deploy the seismic source near the bottom to avoid to have all the water column and sonification. So we have innovation, we have patents on this system. So this is the sources, and this is the streamer which is there. With this kind of seismic, we can have this kind of very high resolution profile. Here we have 600 meters in a very moody mud. So it's also a deep tow because we need a lot of energy to activate this seismic acoustic source, and we have the energy through the cable, and we use the same cable as Victor because interoperability of systems is important for us. If we have a different cable with our systems, it's more cost in terms of management and also training of guys. So we reuse the same. Now AUV. So AUV, it's a long story within Ifremer. So in this line, you will have the operational system, and in this line, number of R&D projects. So I start with this one, which is the Epollard. It's one of the first deep sea civilian AUV, which was rated to 6,000 meters depth in V80 to take pictures on polymetallic nodules fields. So we made 300 dives with the system. So the payload is just a camera. We have a guide rope for surveying in altitude, and the autonomy was 30 kilometers. And we have made 300 dives. So it was an automaton rather than an AUV. It was very simple, running on flat terrain to do pictures of nodules, but it was very successful. It was operational. And since this time, no request from scientists. The request from scientists in terms of AUV is recent within IFREMER. It is in 2000, not before. So during all this period, engineers prepare the future. So we work on intervention AUV, so an AUV with a manipulator in VAT. Then we develop a shuttle. It's an AUV with an ROV frame, which is operated from the ship with acoustic communication. So it's a supervised AUV with inertial Doppler navigation. It was in 97 with Cercel and X-Blue. Each time we have French partners within the industry to help the industry in the developments. At the end of this project, supported by the European Union, we cut this vehicle in the middle and we put in the middle an ROV. This is the swimmer concept, the first intervention AUV. So this is a shuttle, this is an AUV, I will present in detail. And we dock on a docking station on the bottom with this AUV. And when we are docked, we deploy the ROV from the bottom. So we demonstrate this. And we push a button with cybernetics again, with this first intervention AUV with manipulator. I will show you more detailed video later. So that's for the story. And in 2001, scientists request to have survey AUV for deep sea. And we developed two AUVs in partnership with ISE. The model for us is a co-design, and then we license ISE on subcomponents. So we have money back after our investment. And these two AUVs are now very operational. And we also have some development in USV, but we have some limitation to use USV. And today, we have a lot of research projects with multi-AUV swarms R&D. So the idea is to have a lot of small AUVs communicating all together to do more complex tasks. And recently, we developed a new glider because I like to spend dollars, but I prefer to spend euros. So we push a French company to build with us a glider. And at this stage, now we are developing this new HROV. So we present this vehicle now. So the survey AUV, so Asterix and Idefix, 800 kilograms. And within the 800 kilograms, all this part is payload. We have 200 kilograms in a wet part dedicated to science. So it's a limited size, limited weight, with a huge payload for an AUV, 200 kilograms. In these 200 kilograms, you can have multi-beam, you can have spectrometers, you can have what you want. It's very versatile. And for the deployment, the objective was to deploy these AUVs from small ship, non-equipped ship. So we imagine something which is more related to agricultural engineering. It's very simple. It's very marine. It's not a LARS, very complicated, but we have patent on this system. It's a cage, a mobile cage, and this allows us to deploy up to sea state 5, these AUVs, from very small ship. Okay, so I go ahead. So to operate these AUVs, we need 3 operators. Again, to optimize the service. We have flexible payload up to 200 kilograms and the fast data service production with all the software to be able to exploit the data. This kind of map is made 15 minutes after the AUV come back to the surface. So it's mainly survey AUV, so it's mature today. So here you have a view of different kind of sensors. We operate multi-beam, EM 2040 from Kongsberg with water column integration. So here you have bubbles detected, mapping, classical high-resolution mapping, monobeam sounders for fishery. So here you have fish, ADCP, ADV for very precise physical measurements, and mass spectrometer also included. And here you have a view of a payload section. So track records, at this stage we have made 20,000 kilometers in 7-8 years of operation, and the range, maximum range, it depends the speed and the payload, is about 100 kilometers at 3,000 meters depth. We have wings because the idea for us is to operate on very rough terrain. We can climb slopes up to 60 degrees with this vehicle at 3 knots, very close at about 60 meters from above the bottom. It's also for us a system we can adapt for R&D. So in this configuration, we add a middle part here with another canister, and in this canister we have the fuel cell, and here 2 bottles of hydrogen, and 1 bottle of oxygen. And in this fuel cell configuration, we have made 330 kilometers from Marseille in the south of France on Metzi to Barcelona in Spain. So this is a survey we have made with such a fuel cell system. It was original because the interest of the fuel cell, we were able to fill the gas at sea on the deck of a ship. So the big interest here is to be able in 15 minutes to get again 36 kilowatt hours of energy, which is not possible with lithium-ion. With lithium-ion, we have to change the battery or to wait for 8 hours, 10 hours to get again the energy. So this is not operational because a lot of HSE problem with the gas, but it's feasible. We demonstrate the feasibility. So that's for R&D. Again, in the R&D field, this is an illustration of the hybrid intervention AUV swimmer. TRL, it's about 5. We have made several experiments. This is the concept. We dive with an AUV bringing on his back the ROV from the FPSO. We run to a garage which is connected to manifolds, so we have a link through manifolds. We dock on the garage, and when we are docked with the AUV, we deploy the ROV from the FPSO. So we avoid to have a supply ship to operate an ROV on a manifold with this concept. So we made the demonstration, we built a prototype, and now we're waiting for the market. That's a problem. The R&D is there, but the market, not really. And we push the story with a second project named Alive. Again, the idea is to have an AUV able to do the job done by an ROV on the roof panel on a manifold. So we have to run with autonomous navigation, we have to detect the manifold, and we have to dock using acoustic and optic treatment on the manifold and with small manipulators. This is the demonstration we have made with this Alive concept, but it's difficult to change the game because the operational guys will say, I want to be sure you will not lose the control near to my manifold, which is not easy to demonstrate. There is also the problem of the asset. They invest in ROV, it's not time to change. And there is a problem also of time. Time is a non-linear constraint, said by Lewis Carroll, Alice au Pays des Merveilles, Wonderful World, and after Albert Einstein. So it's not time to market, but from a technological point of view, it's feasible. We demonstrate the feasibility. In terms of R&D today, the main effort for us is in communication, acoustic communication, but also optic communication. We benchmark existing solution. This is a wood-sole solution, and we develop also in the optic world new solutions with the Navy, the French Navy, to be able to have 10 megabytes at 100 meters omnidirectional in the black. This is the idea of the optical modem, and we push also new development in the acoustical modem on the side of optimization of the energy. In terms of energy, so it's mainly lithium-ion, real lithium-ion, not lithium polymer, and also fuel cells. Gliders, so I have this park of American gliders for science, but the problem of gliders is not the technology. The problem of glider is the glider man. It's the way to operate the glider. A glider is doing this kind of thing. Each 2 hours, the glider is going back to the surface. If everything is okay, no problem. You can continue the mission. If the glider has a problem, he rings a bell anytime in the day, and you need to have an operator to do the job, to reprogram the glider. So the problem of glider is not the glider itself, it is the way to operate, it's the glider man. So man is still a problem in this system. So here you have some track of our gliders at sea in Med-Sea. But we have also developed some technology for military application with gliders not coming up to the surface, but just getting some information from a buoy, and a glider able to do this kind of trajectory. So to do this kind of trajectory, we had a screw. It's why we call this system an hybrid glider. It's an AUV or a glider, depending the phase of the mission. In this phase, it's a glider. In this phase, you deploy this small screw, and you are running as an AUV. So this is the Sea Explorer system, which is developed in cooperation between Ifremer and a French company named AXA. I forgot the logo here. AXA, which is based near our facility. So this system now is commercial, and it's an opportunity not to only buy American stuff. USV. So in the USV field, since a long time, we were engaged because it's exciting for engineers. But at the end, the main problem for us, we are civilian, is how to use USV from the legal point of view. If you use USV with a ship doing the policy of a water plan for security, there is something strange, because you have a ship here to manage the security of a USV. If it is fully operational, we have a real problem of legal issue in our field. So at this stage, it's mainly not a toy, but it's a perspective, and it's not easy to find the good way to operate. For the example of the wave glider, the way we use wave glider is virtual mooring. So we declare to the authority the position of a wave glider. We say it is within a circle of 500 meters. We declare it, and we say it's a buoy, and we are safe. But to cross the ocean with a wave glider, there is an issue in terms of collision and responsibility. So for us, it's important. Now I will finish with the new development, the HROV. So it looks like an ROV. We have manipulators, 7-function electric manipulators, propellers, etc., etc. But in fact, it is not really this. In fact, it's a mix of ROV function and AUV function. It's why we call the system hybrid ROV. So the first issue is we have batteries on the vehicle. So the energy is not coming through the cable from the ship. And we have two modes of operation. ROV mode with a reversible fiber optics, which is linked the HROV to the ship, and AUV mode with no links to the ship. So what it is? So you have here the two deployments. The ROV deployment, so you have a classical cable, a classical dead weight because we have to compensate movement, then a classical winch in red here on which you can tow the vehicle to recover and to deploy, and in green here a fiber optic, a very long fiber optic, up to 3 kilometers in certain version, and in the nominal version 500 meters. So the interest of this ship can be not DP. So the ship is moving, and here on a tether management system, you manage this length. So the ship is moving, this is moving, but this is managed in permanence, the length of the fiber to avoid the vehicle to be towed by the ship. So that's the idea of the HROV concept. In AUV mode, it's more simple. In AUV mode, you can use your dead weight to deploy telemetry, so you have no problem of noise, no problem of rain, no problem of ship noise, and you operate your vehicle as a classical AUV with telemetry or with no telemetry in a full autonomous mode. For us, the interest is to be able, what we can do with a classical ROV, telemanipulation, from non-DP ship, very small ship, up to 2,500 meters depth. That's the issue. So here is a capability graph of our coastal ship with no DP, let's say 300 meters radius. Here is the dead weight. Here is the winch. Here is, again, the tether, so 3 millimeters fiber optics. And on board, you have a TMS, which is a bit intelligent, with some patent on this. And you manage the length and the tension of this, avoiding to tow the vehicle, to have a vehicle in a quiet situation, to operate with the high rate communication through the fiber. So that's the idea. You are here the fiber, here the TMS, tether management systems. And the advantage of this, compared to other systems where you lose the fiber each time, we can reconnect the vehicle to this buoy here, just winching all the fiber to this position, and then you can tow the vehicle to another position and redeploy the vehicle with the fiber. So it's a reversible system, it's not a losable fiber. So for us, the interest is reduction of cost and the capacity to deploy in deep condition ROV-like system from a very small ship. So here's some view of mission. So in AUV mode, you can imagine this configuration with no manipulator. Everything is scalable. So you operate it as a classical AUV. Compared to the survey AUV, Asterix and Idefix, the big advantage here, you have DP function in the propulsion architecture. So you can have a DP of a vehicle on the bottom. You can run very slowly, and you can also follow cliff, which is not possible with survey AUV. If you want to map a cliff, it's well adapted. So that's the idea. Again, with the multi-beam, and here in a situation with the fiber this time and telemanipulation. So the vehicle is under integration today. So on board, we have a battery. We have 20 kilowatt hours of lithium-ion battery. We have a TMS to manage the tether, and then classical things. We are just tracking the weight and tracking the energy on the components we choose. So we need to develop also new components because we have this energy consumption to manage. And here you have the main characteristics of the vehicle in two configurations, light configuration and heavy configuration with manipulators, so up to 1.7 tons. And you have airspeed and the autonomy in full autonomous mode with multi-beam is about 12 hours, and the autonomy with telemanipulation is about 8 hours at 2,500 meters depth. So it's a Swiss knife system with capacity to adapt the payload. You have a basket. You have all the capacity of classical ROV. And here is the demonstration from the economical point of view. The commercial day rate of a DP ship, the smaller four-framer able to deploy a deep ROV, Victor, it's X. If I take a small ship, 35 or 40 meters length ship with a classical class 2 commercial ROV, you divide this cost by 2 because the ship is less important. But you need a DP ship to do this kind of operation at 2,500 meters with this kind of ROV. And with HROV, we will divide by 4. Okay, I'm close to the conclusion. So for us, a new objective and a new innovation, we have a set of points. We have to deal with new requests, with more and more complex tasks on observatories, instrumented sites for scientists, more and more habitat mapping because regulation, so we have to do the map. So we have to optimize the cost because we have the same money from the government to do more, so we have to optimize the tools. It's also the case for status of marine waters, etc., and more quantitative and repetitive survey are needed. Sorry? Okay. So we have also to optimize this cost of possession because the cost and the requests are there. In terms of technology, it's more and more autonomous system with advanced control and intelligent mission programming. We are also engaged in fleet management and environmental-based control systems, new energy sources, embedded system optimization, smart sensors, electronics, MEMS, new actuators, etc. But the keyword at the end is smart, hybrid, and cooperative systems. It's the way on which we are pushing research, not only within IFREMER, but also within the academic partnership in France, in Europe, and in the world. So I finish. So this is a view of No-Till, filmed a few years ago by the Alvin. So it's a meeting of Alvin and No-Till in depth, just to illustrate that great idea born when we met. And I'm very happy to meet you here in Brazil. And I hope we can discuss more during the day. Thank you.